Okay. Thank you all for coming this morning. My name's Hugh Blemings. I'm the Executive Director of the OpenPOWER Foundation, and this is my colleague.
Alistair Francis from Western Digital.
And we're delighted to introduce you to the first OpenISA mini-conference. Before we kick off, though, we did want to do an acknowledgement of country. We gratefully acknowledge that we meet today on the traditional lands of the Yugambeh people, and we pay our respects to their elders past and present, and leaders emerging. So a little bit of background. This is the first OpenISA mini-conference for linux.conf.au, and Alistair and I were discussing it. We think it's probably one of the first OpenISA mini-conference sessions anywhere. We've had two of the main OpenISAs, RISC-V and OpenPOWER, on the same program together. So perhaps a significant time for our overall ecosystem. A little bit of housekeeping. If you're presenting when you start your session, please just wait for a thumbs up from the AV team that they've got the recording going, so we're able to capture the entirety of the event. If we do have Q&A, which we hope to as we go through the various sessions, please wait for the microphone before you pose your question, because that way it can be captured for the audience. If you're a presenter and you note that the question hasn't come through the microphone, perhaps you could just repeat it. The way we've structured the event as far as possible is the breaks should line up such that you can move between the mini-conferences. The main breaks at lunchtime and afternoon tea are concurrent. If possible, though, if you do want to leave in between, please wait for a break in the actual sessions rather than storming out midway through. We do have a wide range of topics throughout the day. Essentially what we've got is some RISC-V-ish sort of stuff this morning, a lunch break, some OpenPOWER related sessions in after lunch, and then afternoon tea we've got a bit of a mixture of different topics that apply to all of them. And what's not a good mixture, I hasten to add. What we didn't have time to include, because it was a last minute inclusion, we'll have the indomitable Tim Ansell doing some stuff on OpenFPGA tool chains to round the day out. And I think with that, I shall stop talking and hand over to you, Alistair.
Thanks. So we'll do a quick introduction on RISC-V for anyone who doesn't understand it all. So the first thing is RISC-V, not RISC-V. There's a lot of confusion about that. And so RISC-V is an ISA. It's not a CPU architecture. It's not a CPU, it's the instruction set architecture. So there's a lot of confusion about that. The ISA is open, but you can use the OpenISA to make a closed CPU. There's always a lot of assumptions that people think everything RISC-V is open source and it's always going to be open, but the ISA is open and it just allows you to use it to do whatever you want. The same way that lots of like BSD style licensed software works, for example. And so the ISA is incredibly small. It's a handful of instructions to load and store basically. And then on top of that, you kind of add extensions. So everything has to be either the integer or the embedded. Pretty much everyone uses the integer one. It's small enough that no one really uses the embedded one. And then on top of that, you add multiply, divide, atomics, things like that, floating point, compression. I'm not going to read them all out, they're on the slide. So that's your kind of basic ones, what you need to do kind of modern day computing. And on top of that, you have virtualization, vector extensions, bit manipulation, some more advanced ones. And there's a whole heap of ones being discussed as part of the RISC-V Foundation. And so RISC-V, and the general extension is the one you'll see commonly. So it's M, A, F, and D. So Linux generally requires G and C, so the general extension plus compressed instructions in 32-bit or 64-bit. So RISC-V is aimed at everything from small systems to high-performance computing. That's why we have this kind of modular extension system. So if you have a really low-end thing and you don't need multiply and divides, or you don't need atomics, you can make a CPU without atomics. And if you have some high-performance computing, you can have virtualization and vector extensions and all these things and do whatever you want. So there's lots of CPU implementations available today. This list is a little out of date. There's just too many, kind of run off the end of the slide. So Sci-5 is the big one. I think anyone in the RISC-V industry knows about Sci-5. They're the spin-off from Berkeley. So they have options. Then there's Boom, Rocket 64, QEMU has a great implementation. There's IBEX, and a whole range, Litex, there's a whole range of different ones. So if you're interested, you can basically, in trying RISC-V today, you can basically find an FPGA and then find a design that will fit on that FPGA. There's something for every type of thing. So if you have a super expensive FPGA, you can put a giant core and boot Linux. If you have a FOMU, a little tiny one that fits in USB port, you can find something and boot embedded, some embedded OS on there. And so RISC-V is heavily backed by a whole range of companies. Western Digital is a big one, NVIDIA and Sci-Fi are two other well-known ones. So why? Why RISC-V? We already have all these architectures. Why do we need yet another one? So RISC-V is OpenISA and the first OpenISA. There's now another one. But it allows anyone to modify the ISA. So this means you can use it to add custom instructions or take things out that you don't need, things like that. So it allows you to modify it and customize it to your use case without shipping these black boxes and signing NDAs and paying some other company a fortune of money to add instructions or let you add instructions. So it allows you to customize it like that. And even within the spec, you can say, make a core that you optimize for your use case that you know you're going to do. Without breaking the spec, you can optimize atomics, for example, and maybe you don't care about these other ones that take and that you don't use, so you make them take longer. It allows for security audits. This is coming up a lot more and more. Who knows what's in something you buy from a black box vendor? This means you can look at the source. If you have your own fab, you can fab it, but that's unlikely. But you can at least look at the original source and see what it's doing, see what's going on in there. You don't have to trust that there's no speculative execution issues. You can verify that yourself. So there's lots of different things there. It allows lower costs. Again, you don't have to go pay some company a huge amount of licensing fees to be allowed to use it. You can start with it as a hobbyist. You can go download one from the internet on GitHub that has a whole heap of reviews. I think everyone in this room knows open source can be really good. So you can take that, it's already been looked at, you can look at it yourself, and then you can get going with it without paying a whole heap of money. And allows this community-driven development approach. So we've seen, especially in the last year or two, issues with, again, these big companies that say, trust us, it's going to be great. And it's not always great. So now you can look at it and the community can contribute and you can have a whole range of ideas from a whole different people. And maybe someone does say, hey, maybe that's not the best idea. You might get better performance, but it opens up this whole range of other issues and you can discuss trade-offs and whatever else, right? It's all in the open. It's not behind these closed doors of trusting someone. So the RISC-V Foundation decides on the final specs, so anyone who's a member can vote on that. It's an open process. It's getting more and more open, I think. I think it's free for individuals to join. So if anyone's interested, you can, again, a thumbs up. It's definitely free for individuals to join then. So you can join, you can watch, you can read, you can comment. The foundation will eventually vote on it. So some decision has to be made. We can't just talk about it forever. But yeah, so if anyone's interested, definitely talk now. Don't wait for 10 years and then when someone makes a chip and then say, oh, I knew that was a bad idea. Now's the time to say it. Oh yeah, the task group mailing lists are now, I think now public. So they used to be members only. They're now public for everyone. So even if you're not a member. So how can you use RISC-V? So the main answer is QEMU. QEMU is awesome. It's the best thing ever. If you're not using QEMU, you should start using QEMU. QEMU supported RISC-V since version 3. We're now at 4.2 was just released, so the support has only improved. If you haven't seen QEMU run before, it's amazingly quick. It's quicker than any FPGA, and maybe as quick as some of the ASICs if they're not as great. So the other option is the HiFab Unleashed, which is the bottom kind of one board there. It's unfortunately hard to get and very expensive. And then you also need the micro-semi expansion board, which is the one on the top, to get PCIe. So this is a demo one of my colleagues did, running RISC-V with Fedora, and SATA attached SMR hard drive, display out over a GPU and USB input. We also have Linux running on a $5 board behind us, but it's no MMU Linux, and the user space just prints hello. Because you run out of, your 8 megabytes of SRAM run out very quickly. So it's super expensive. So there are FPGAs. If you're interested in FPGA development, definitely look at that. Otherwise, QEMU. So I think that's it for me, so I'll hand it over to Hugh.
Nice one. Thanks, Alistair. So, in the interest of full disclosure, we kind of took the whole open source thing perhaps a little bit to an extreme here, because Alistair and I collaborated on the slides, to his great credit, he had the RISC-V pieces together before I'd got to that. I've got a couple other sessions on the go. So I'm reading through Alistair's slides, and actually this is kind of all the same things I want to say about OpenPOWER pretty much. So you'll actually see a distinct similarity between the three slides that we'll present. So what is OpenPOWER? So OpenPOWER is a mature 64-bit RISC ISA. It's got its roots back in PowerPC and IBM Power. And as of August 2019, so just a few months ago now, it was released under an open license. So it's now available to use royalty-free with a pass-through license, pass-through patent license for compliant cores from IBM, which is kind of significant if you're going to invest in building a chip. The ISA extensions and changes themselves will be done through the OpenPOWER Foundation, the organisation I work for. We're in the process of standing up a working group to facilitate that. And when we talk about maturity, I guess it's maturity not only in a hardware sense, but also a very mature software ecosystem. Power is actually one of the oldest non-x86 ports of the Linux kernel, as an example, the GNU toolchain and so forth. In contrast to our friends in RISC-V, it's a relatively complex ISA, and the cores that accompany it. It is targeted more at the mid-performance through to server class and HPC applications. So it is a complex core. It's got a lot more transistors in even a basic implementation than RISC-V does. From a silicon standpoint, currently our silicon power silicon from IBM systems for another 10 or so vendors, but based on the conversations we've had since August, when our phone kind of started running hot, I fully expect that we'll see silicon from other vendors announced in the course of 2024 production in the following year. Courtesy of a team at IBM, we also have a soft core called Microwatt, which some of you may have heard of. That was released late last year as a proof of concept. It sort of started off as an engineer at IBM wanting to learn VHDL, and personally I would have just blinked the lead. They went and wrote a whole static integer soft core instead. There are multiple companies backing OpenPOWER itself. Our platinum members at the moment are IBM, Google, Inspur, Yadro, and Wistron also produce systems. I guess why OpenPOWER, and this is where you really see the similarities in a lot of ways with RISC-V. Similar to RISC-V, the OpenISA allows anyone to modify and experiment with the ISA, but most of it builds into an existing and long-established software ecosystem. So on the software side of things, a lot of those hurdles have already kind of been bridged with OpenPOWER. We allow customization for specific applications. The feedback we've had, and certainly what we've seen in the field so far, is a lot of the interest in building those specific customizations around the ISA are actually more in the accelerator space. So HPC organisations and vendors who want to build FPGA accelerators, add a few instructions into the base ISA to facilitate that and run from there. And like all open ISAs, it allows security audit and inspection. An area where it's a little different is, I guess, on the experimentation side, the Microwatt soft core I mentioned earlier. Well, that'll run on about an $80 FPGA board, and the crew behind it are working on getting that onto more and more compact boards as time goes by. But you literally have the same tool chain with admittedly different compiler flags running on an $80 FPGA all the way up to the number 1 and number 2 supercomputers in the world. So it's a lot of that tool chain side of things is already really taken care of. The community-driven approach, not dissimilar to RISC-V, though. There'll be some subtle differences in the way the work group is instantiated within the OpenPOWER Foundation, but it will provide a means for anyone to provide input into the ISA. And I guess one of the things that often comes up, particularly from journalists who are always kind of looking for a bit of a tagline, is RISC-V a competitor? Well, no, I think we see them as complementary. At the moment we're going after in different sort of spaces, and we see the two as really being quite complementary. In terms of how we access OpenPOWER, we'll also a shout out for QEMU. There's good mature Power ISA support in QEMU. You can go online, get cloud access from a number of providers who provide power systems running typically on Power 9. There's a bunch of Power 9 hardware out there in the market today. Perhaps the most affordable is the little micro ATX form factor motherboard shown there that with a Power 9 CPU is about $1,200 US, runs all the standard Linux distros. It's an entirely open source software stack and an entirely open hardware design as well, all the way up to server class hardware from a bunch of different manufacturers were mentioned there. There's also an FPGA soft core, which you can run under under GHDL, or you can actually put that on something as small as an Arctic 7, and I think Anton's session this afternoon will be talking about that in part. Numerous older systems out in the out there as well, and also a bunch of hardware based on our close relative, the PowerPC cores, including everything up to spacecrafts and all different things running PowerPC. I think that's it from an OpenStaff standpoint. So again, I'll say welcome, and I'll hand back to Alistair to introduce our first RISC-V talk. Thank you all for your attention this morning.
So Atisha's going to start talking about the RISC-V software ecosystem now and for 2020.
Let's do the customary mic check. Oh, it's working.